Hello and welcome everyone for the next session of Introduction to Biomedical Optics from Theory to Applications. On today's session, we will talk more about how if we actually develop a new system, how we can actually put it into clinical trials. If we put it into a clinical trial, how we will get to know whether our system is faring as compared to the clinical systems which are already present in the hospital. Right. So the tool that people usually use to compare a new imaging system, whether it is optical or any other modality, it could be X-ray, MRI, or it could be a PET. It is through a term which is known as biostatistics. So today we will learn about how you can actually perform some biostatistical analysis and compare your new modality as with the present clinically validated imaging systems. Okay. So the conundrum is, for example, you have a new imaging modality. It is an ABC modality. Let us name it as an ABC modality. It's kind of a generalized name that we have given. And a person which is having who is having a complaint of a pain in a colon, that is part of the intestine, had a recent trip to the hospital. He underwent two imaging modalities, right? Like for example MRI, which is considered to be a gold standard. So a gold standard means that imaging modality which is kind of considered to be having a very high accuracy, right? So let us assume that MRI is a gold standard in this particular context, right? When you go for, if anyone goes for a kind of a cancer diagnosis, no image, most of the time it is a biopsy is what it is a gold standard. But let us, in this context of learning biostatistics, let us assume that MRI is a gold standard and we are trying to compare our new modality, that is ABC modality, on to this gold standard. So we try to compare our new modality as compared to the with respect to the gold standard MRI technique. Okay. So gold is nothing but with to do with the gold material. It's just a terminology, right? So the way to do that is biostatistics. So let us now draw one table. So this is a table that everyone draws in the case of biostatistics. In the first column, you actually put the results from the MRI, that is the gold standard, which we will term as ground truth. The first row, let us put it as ABC modality, that is the results from the ABC modality, imaging modality. So now let us populate the other part of the table, that is if a person going for an MRI is found to be positive, let us term them as capital P. If the person who is found to be negative through a gold standard, we will term it as negative N. Then we have in the ABC modality, which is the new modality that we are proposing, if the person is found to be positive, we will tell it as predictive positive. So we don't tell it as positive, but we will tell us that it is predicted to be positive, PP. And if the person is found to be negative using our modality, we are going to tell it as PN, that is predicted negative. Okay. So now let us try to understand that if a person is going and it is found to be positive by a gold standard, but at the same time it is also found to be positive by our own modality, what is the terminology of such kind of incident? So there is a technical term, and that technical term is true positive. That is, the patient who has been diagnosed with a particular cancer, for example, by the MRI, which is the gold standard, and the same diagnosis of being a cancer has been generated by the new modality, that is ABC modality. Okay. So then that case is known as true positive. However, if the person is positive, is found to be positive by the MRI or whatever is the gold standard, but it is found to be negative by your own modality that you are trying to propose, that is known as false negative. Similarly, when the person is found to be negative by the gold standard, that is MRI modality, but found to be positive by your modality, that is like falsely it is positive, right? So that's why it is known as false positive. Similarly, if the person is found to be negative by the MRI and with your own modality, new imaging modality, both is found to be negative, then it is known as true negative, right? So these are the four, and it will be always between these four sections, any of the classes, any of the results would be from these four sections. Okay, so now one can actually find out the sensitivity, that is sensitivity which is TP, that is total number of patients which were found to be positive by both gold standard as well as your new imaging diagnostic modality, that is TP, divided by the total number of patients to be found to be positive by the gold standard, that is both TP plus Fn. So here P is nothing but equal to TP plus Fn. Similarly, sensitivity is defined as true negative, the number of patient as true negative divided by total number of patient as negative. Here capital N is nothing but the summation of Fp, that is false positive plus true negative. Similarly, we have another terminology, that is positive predictive value, that is PPV. So the PPV is defined as TP, that is true positive, divided by PP, that is predictive positive. Right now, predictive positive means it's a summation of both true positive plus false positive, right? So we will have an example so that you will get to know about the how we are defining all these terminologies. And then this negative predictive value. So the number of subjects which were termed to be who were given a result as negative by our own modality. So that is given as a ratio of true negative, number of patient as true negative, divided by the total number of patients found to be predicted to be negative, that is Fn plus Tn or Pn. Okay. So the accuracy is defined as true, the number of patients as true positive plus true negative divided by the total number of patients actually. So that is positive plus negative. Okay. Okay, so let us again revisit the conundrum that we were discussing. We want to compare it. How do we compare it? So let us see one example, right? So there are total of 2030 patients, you can see over here. So which were tested, and out of that around 30 were found to be positive by MRI, and around 2000 were found to be negative through MRI. Okay, so in this case, the data is already given to you. Okay, that the predictive positive is 20, predictive negative is 10, predictive positive in this column, this cell has 180 value and this cell has around 1820 value. Okay, so this is nothing but true positive, this is false negative, this is false positive, and this is true negative, right? So these numbers we have already mentioned. So from these numbers, can you calculate sensitivity? You can actually pause this video and try to find it by yourself, just to get an idea of what are the values of sensitivity, specificity, positive predictive value as well as negative predictive value, and as well as the accuracy as well. Okay, so I will just go ahead and find it. So you can see that the sensitivity is TP, that is 20 divided by the total number of patients who were found to be positive, that is 30, which comes out to be 66.7%. Similarly, specificity was defined as true negative divided by total number of subjects to be found negative, that is 1820 divided by 2000. Okay, and that came to be very high, that is okay. So the specificity is defined as true negative, that is 1820 divided by total number of negative subjects, that is 2000, right, and that comes to be 91. And after some time we will also tell about what does it mean that having a diagnostic system having a very high specificity as compared to very low sensitivity. Okay, we will talk about a test case. Over here, positive predictive value comes to be having a ratio of 20 divided by total number of positively predicted, that is around 200, that is around 10%, and negative predictive value comes to be around true negative divided by total number of subjects who were found to be who were predicted to be negative, that is around addition of both of them, that is around 1830, which terms comes to around 99.45%. Okay, and the accuracy you can actually find it by finding in the numerator, that is what are the number of truly found to be positive or negative, that is 20 plus 1820 divided by the total number of subjects, that is around 2030. Okay, then that comes to around 90.64, which is like a very high number for an accuracy, right. So so let us just try to understand what do we mean by these terminologies. What do you mean by sensitivity? What do you mean by specificity and PPN, PPV, NPV, and accuracy? So sensitivity is something like how good is the test at finding out what you want, what you are looking for. Okay, so if the sensitivity is high, means your test is good to find what you want. Specificity is the kind of an opposite, like how good is your test to avoiding things that you don't want. Okay, so once we give an example, it will be more helpful. Positive predictive value is that if someone is found to be positive, then how much you can trust that data. Okay, for example, having a PPV value of very high means that I can trust the data if I am found to be positive. And similarly goes to be negative predictive value. If someone is found to be negative, how much can you trust that particular negative results, right? So if over here you can see that the predictive negative value, negative predictive value is like very high, so means I can trust if I am found to be negative, I can really trust that data. Okay, and accuracy, as you see on the top side, is kind of a broad term, a kind of a kind of measure which can actually tell about the reliability of the results. Okay, so these are the few parameters of few founding blocks of the biostatistics, which is used for a diagnosing of any system. So let us give an example. If most of you might be aware of COVID, and during COVID there used to be two different techniques that people use. So one was RT-PCR, that is reverse transcription polymerase chain reaction test, other is a rapid antigen test. So let us see what happened in both of them. So the RT-PCR of course was costly, it was time consuming, and it was highly sensitive. Like we can actually find out if someone is found to be positive in this, means you are definitely suffering from COVID. Okay, and on the other hand, we were having a rapid antigen test, which was actually cheap, it was less time consuming, but it was very low sensitivity. But there was something known as specificity, which was very high, more than 90% in the case of rapid antigen test. So what does it mean? It means that if something having high specificity means if you are found to be negative, okay, then you cannot be sure whether you are suffering from COVID or not, right? But if you are found to be positive in rapid antigen test, means that there is a significant chance that you are having a COVID. Okay, so that is the meaning of specificity. Okay, yeah. So one more technique that people use in the field of biostatistics to differentiate between the gold standard and the new imaging modality is using a receiver operating characteristics. So receiver operating characteristic is nothing but a plot between 1 minus specificity and sensitivity. So x-axis is 1 minus specificity and y-axis is the sensitivity, right? So when you see the receiver operating characteristics, that is ROC, the straight line actually can be made in the center, and that actually tells about a random case or kind of random classifier. So it's kind of a 50-50% chance that it's kind of a, but no one would like to have 50-50% chance if someone goes to a hospital to get diagnosed with tuberculosis, for example. No one will like to have the accuracy of the test to be like 50-50%, right? So they want very high accuracy, like more than 80, more than 90%, right? So if found to be if found to be diagnosed with tuberculosis, then proper medicines could be actually processed, right? And ROC actually helps you to find out this sensitivity and specificity based on from the graph. So you can see this is the one diagonal line, and that diagonal line is the 50-50% case. Now you actually can go forward, keep on going forward, like if you go towards this one point over here, that is the highest value of the true positive. As you keep on going away from this 50-50%, how much more bend that you can actually have of this ROC is the best, right? So if you go towards more and more better. Okay, if you are surviving somewhere close to this, then it's like 50-50%, right? Which we don't want actually to go. So more the bend, it's the better. Okay, so now let us try to understand how can we actually plot this receiver operating characteristics. So this could be plotted in any of the computing tool like Excel, for example. So I will show you how we can actually do it in Excel sheet as well. Right. So let us see one example. This is my own work that we published, and for example, if someone want to go for a breast cancer diagnosis, the first thing that happens is a triple assessment. That is, one first go to clinical breast examination, then ultrasound and X-ray mammography. If found to be positive in these cases, then actually they perform ultrasound. This is, you can see this ultrasound system, and this is a core needle biopsy. So it's ultrasound guided core needle biopsy performed. So you can see this is a cross section. So this is the place where the tumor is located. So this ultrasound actually goes through ultrasound waves goes through and kind of images the suspicious tissue, and then with core needle biopsy we get tissues like this. This is a tissue with a thickness of 1 to 2 mm and a diameter of around 5 mm. So basically they slice it into hundreds of micrometers. So they freeze it first, make it into paraffin, then slice it into hundreds of micrometers, then deparaffinize, then they stain these tissues and then see under a light field microscope. And this is the traditional approach. So in addition to this, can we have another modality like hybrid spectral IRD system that we propose, where you can just assume that this is the tissue and we are shining a light from here and then detecting on the other side using different wavelengths, right? So from this system we get a result like what you see on the right hand side. Okay, so the first column is for the number of patients, that is around total subjects tested was around 22, out of which around 11 were normal and 11 were cancer. Okay, so the second column that you see is a quantified parameter. You can assume it as, for example, you are giving 20 volts from this side, there is a medium and you are getting detected to be 5 volt, 3 volt, something like that, right? So it's a quantified parameter, right? So you can pause this video again and just try to understand if you can find some kind of a trend. Okay, so I hope you have paused the video and tried to find out, and what you find out over here is that cancer is having higher values of quantified parameter as compared to the normal. So normal has lower number of values of this parameter as compared to the cancer. So what we do is that we now make it into ascending order. So you can see this is now in ascending order, everything. Okay, and then once it is in ascending order, your job is to find and cut off which actually can help you to differentiate normal and cancer, right? So the game is to find the threshold. Okay, if you are able to find a very good threshold, then you can actually say that your sensitivity is very high and specificity is very high as well. Okay, that's good. So okay, but how do you find the threshold? Okay, so the threshold, how you find the threshold is how you you can actually take help of the ROC, that is receiver operating characteristic. To get that ROC, that is receiver operating characteristic, you can also put this data into Origin Pro and you get ROC. Okay, it's a very simple way of doing it. What I am going to show you is the approach that we implemented in Excel sheet. If you don't have Origin Pro, you can try with Excel sheet as well. So in Excel sheet, what you do is that you actually put the values in ascending order, all this data, quantified parameters. Okay, then you add a column that is cancer and normal, and whichever number was associated with whatever value. So for example, 1.26 you can see is associated to normal over here. You can see the same thing. You just keep on populating it. For example, 7.77 was given to cancer. So 7.77 I have given 1 in the cancer column, right? So on and so forth, right? And grand total will always be 1 because this is sum of both of this, cancer and normal, which should be always 1. Okay. So here you can see this is cancer and normal, and then you can actually find, so there is a formula that you can use in Excel sheet, so of calculating sensitivity and specificity. So you can just implement that formula, okay, and then you can find what is the sensitivity and specificity for all the cases. Okay, so it's again, it's kind of a formula that you just need to put it, and then you get these values. Now once you are over here, your objective is to find the threshold with which you can differentiate normal and cancer, right? Now for example, you put the threshold over here. Okay, so over here you put something between 5.5 and 7.2, that is a threshold of 6.2. So let us see what is the case of 6.2. If you put the sensitivity threshold of 6.2, what is the sensitivity, what is the specificity, right? So if you see that the sensitivity is giving us around 100%, it's very high, right? But the specificity, which is actually this column is 1 minus specificity, so your specificity is actually 1 minus 0.45 into 100%, right? So it comes around 54%, which is like very less. Now a problem because sensitivity is high, that's what we want, but specificity is less. Now let us choose one more threshold over here, this line over here, and you see that the threshold is between these two values, which is around 8.7. This gives a sensitivity of around 0.63, that is 63%, but specificity is kind of very high, right? So this is the opposite of what we discussed earlier. Sensitivity is, in this case it is lower, but the specificity is very high, but that's again a challenge. So we have to do some kind of trade-off so that sensitivity is also relatively high and specificity is also high. So we choose something in between, we do a trade-off. For example, this is the threshold, we choose around 7.8 in this case, and we get sensitivity of 100% and specificity also not that bad, which is around 81.82%, which is kind of very good, right? So it's a trade-off between sensitivity and specificity that we do along with these numbers. Okay, and then you can draw this ROC, that is, you can draw in x-axis is the specificity, 1 minus specificity, and y-axis is your sensitivity, and you get an ROC curve like this. Okay, it's not a kind of a nice smooth curve that you saw some time back. If you have a very large number of data set, 100, 200, then you get a very smooth curve like what you had seen in some time back. Now I have only 12 numbers, right? So that's why it is having such a low number of such a crude jumps. Right. Now if you can see from this ROC curve itself, I can actually find what is the best sensitivity and specificity, right? For example, I will always choose this guy because after which there is a drop in sensitivity, right? I will choose this guy which is actually giving you a sensitivity of 100% and specificity of 81.82%. If I choose a point lower than this, my specificity is going to stay constant, that is 81.82%, but my sensitivity is going to decrease, right, around 90.91%. So I from this ROC curve, of course I will choose this point itself, right. So based on the ROC, you can actually choose what is the best sensitivity and specificity, right? So you will see there are a lot of cases, and it depends from case to case. For example, this is the one more example where you see the false positive. This is the area under the curve. So area under the curve is also an important parameter which is used to differentiate normal and cancer, like how much is the trust of the results. So higher the AOC value, that is area under the curve value, means that it is higher chance of predicting correctly whether it is normal and cancer. Okay. For example, in this case you can see this point that you choose over here, it has a sensitivity of 70%, and the specificity over here is around 1 minus this value, that is comes around 94%, right. So this kind of ROC would always be there when you actually discuss any paper of any imaging modalities, with new imaging modalities, describing the validation study with any gold standard. So you will ROC, sensitivity, specificity, you will always see, right. So today we covered, just to summarize what we covered is, we started with the basic foundations of biostatistics, that is how you can make a table which gives you sensitivity and specificity, negative predictive value, positive predictive value, and accuracy. And also we talk about receiver operating characteristics, with which you can actually plot the ROC, find area under the curve, and also find have a trade-off between sensitivity and specificity. Okay, thank you. Thanks a lot.